we go. All right. Make it bigger. Can everybody see that? Is that good? All right. So chapter 2 obviously starts talking about descriptive statistics. What we're going to do in chapter 2 is we're going to learn about descriptive statistics. We're going to use a lot of these techniques that we learn in chapter 2 for the rest of the semester. Some of them we're going to use a little bit more often than others. So once we get to the ones that are important for you to make sure that you remember and know how to do for the rest of the semester, I'll make sure I highlight those to you. But first, what we're going to start off are just different ways to display data. One of the first ways that we're going to learn about is the stem and leaf diagram, which is something that came up last class as well. Here is the book-provided definition for the stem and leaf diagram. I'm not going to read that definition for you guys. You guys have it available there. But what we are going to do is we're going to have an example right here of how to create a stem and leaf diagram. So let's go ahead and do that. So a stem and leaf diagram is exactly what it sounds like. We're going to create a stem, and then from this stem we're going to have different leaves that grow from it. And the way that we're going to do it is this. We're going to have this vertical line right here. And on the left of this vertical line is where we're going to put the stems, and on the right of this vertical line is where we're going to have the leaves. Now the way that this works out is this. We're going to start off with the number 0 right here. And you can think of the number 0 as being in the tens place of any number, right? So if you have two numbers, or let's just say you have a number that has 2 digits, so let's say like the 15. This over here is the tens spot, and this over here is the 1 spot. The 0 that I just made right here is going to be in a 10 spot. So basically what we're going to do is we're going to create a diagram that looks something like this, where this right here is our vertical line. And on the left-hand side, we're going to put our 10 spot. And on the right-hand side, we're going to put our 1 spot. So it's going to look something like this. Then after we make this vertical line and put the tens on one side and the ones on the other, we're going to go through our data set, these numbers up here, and we're just going to record those, and as we're going to see, it's going to create something that kind of looks like a stem and leaf. So what we're going to put right here are going to be all the single-digit numbers. So we have the number 6, we have the number 7, so we're just going down the list. We have the number 5, we have the number 1, we have the number 5 over here, and we also have the number 6. Everybody good with what I'm doing so far? Well, now we're just going to go up to the next 10 spot that we could possibly have. We could have the 2-digit numbers that start with 1. So what number would I then write right here? 3, right? So here we have the number 13, so I'm going to have a 1, and then here I'm going to have a 3. Now I have an 18, is that my next number? So here I'm going to have the 1, and I'm just going to write the 8 right here. Right, is everybody good with what I'm doing up here? So then that's the 18. What am I going to write next? 7 for this 17 right here. And what comes next? Anything else after that? You guys get the gist? All right. Take another minute or so for yourself and see if you can finish off the stem and leaf diagram by yourself.
It doesn't ever have to be in order.
We haven't gotten to that yet, but I'll talk about that here in just a second.
What's the thing you talked about yesterday, like the frequency relative data table or whatever?
Talked about the relative frequency, and we also talked about the data frequency table.
Yeah, okay. So I remember saying it was similar the way it was taught. I feel like it is similar in a way though, because like in the data you kind of have to, and you can't leave a number out. So you represent the numbers in a different way, so like you can't leave one out. Like they all have to.
Yeah. So once we get done and we have it up here, we can compare and contrast it to the data frequency table. Yeah. So let's go ahead and finish off. Does anybody need any extra time to finish off the stem and leaf diagram? All right, so then here we would have the number 2 for the 20s. we have the number 20 right here, the number 28 right here, and we also have the number 20 right here as well. Then the next one we would have is 3 for 30s. We have 130 number right here, which is 31. And here we're going to have the 40s. If we go through, we have the number 43, and we have the number 46. So we'll make it 3 and a 6 right there. And then we've used all of our numbers, right? Is everybody good with this stem and leaf diagram? All right. So now the question is, do these numbers right here have to be in order? Now, the convention is yes, right? The convention is that we should write these numbers right here, which is what we're going to call as our leaves. Convention is that we should have those in order. Now, technically speaking, it's not incorrect to not have them in order, right? If you want to compare this to an English class, it's kind of like using the word ain't in a sentence in English class, right? It's not quite right, but technically speaking, ain't is in the dictionary, so it's completely fine to use that as well. But what we should try to do is we should try to have these things in order. Another convention, and this one is a little bit less used, is what happens if we didn't have, say, a number in the 30s, right? Then technically speaking is we could either have this spot right here blank, or we could just not include the 3 right there, right? So generally speaking, we would simply just not include the 3 and just go straight to 4. But it's obviously not incorrect if you just use that, just leave this spot right here blank, right? Especially whenever we're working in large data sets, right? Let's say that we didn't stop right here at the 40s, but we went on to like 40,000, right? And we just kept going and kept going, which means that here, technically speaking, we could also keep going, and then over here, we would eventually have something that looks like 10 and 11 and 12 and so on and so forth. If we went all the way to, say, like something like 40,000, right? We just keep going and going. But let's say in that data set that goes to 40,000, let's say we have a bunch of numbers in the teens and a bunch of numbers in the 20s, and then we skip a whole bunch of them, and then we go have a whole bunch of numbers in the 50s and the 60s and the 70s, and then we skip a whole bunch more. Well, if we included that 3 and we didn't have any numbers over here, we would just end up with a huge stem and leaf diagram where there would just be a bunch of blank spots. Technically speaking, if we went up to 40 million, there could be potentially a whole lot of lines that were simply just created out of blank. That doesn't really help anything out, right? So a lot of times we would simply just leave those numbers out, and we would just skip whatever digits that aren't included in our data set. Make sense? Cool. So the way that you're going to see stem and leaf diagrams in this class, though, is that it's always going to be well ordered. So let's go ahead and order this right here. The only thing that we're going to do is we're going to put these in numerical order from smallest to largest. So we would have 1, and then have 5, 5, 6, 6, and 7. And then here we would have 3, 7, 8, and 9, 0, 0, and 8, 1, 3, and 6. So here we would have our stem and leaf diagram. This is the way that you're going to see it in this class. On the right-hand side, you're not going to really see it on this way presented to you as it is on the left-hand side. However, you will see data presented to you this as a stem and leaf diagram on a test in this class. So you should understand how to read a stem and leaf diagram. Particularly what you're going to have to do is you're probably going to have to find something like the middle number, right? As we're going to talk up here in a little bit, it's going to be called the median. So whenever you see a stem and leaf diagram, you should be able to identify how to find the middle number, right? You should realize that this right here, even though it looks like a 36, technically that's 2 numbers, right? That's not 1 number right there. Right? Everybody good with how to read a stem and leaf diagram? Bless you. All right. The next thing that we're going to do is we're going to create frequency histograms. A frequency histogram, just like it says right here in this definition, is a graphical device showing how data are distributed across a range of their values by collecting them into classes and indicating the number of measurements in each class. So let's do that here for a second. What a frequency histogram looks like is it looks something like this, right? Where it's kind of like the first quadrant if you're looking at a Cartesian coordinate system, right? Just this upper right-hand side. And what we're going to do here is this. We're going to create classes, or simply just here, we're going to say we have the number 1, we have the number 2, we have the number 3, we have the number 4, and we have the number 5, and the number 6. So I'm going to go ahead and put these down here. Here's the number 1, here's the number 2, here's the number 3, here's the number 4, here's the number 5, and here's the number 6. So I just realized that the question came up earlier about comparing stem and leaf diagrams to the data frequency table, right? Let's do this one right here so we can also compare this one to the data frequency table, and then we'll compare both the stem and leaf diagram and the frequency histogram to the to the data frequency table. All right, so here are our classes. These are the categories that these numbers could fall into. What we're going to try to do is, just like we did for the data frequency table, we're going to try to identify how many of these numbers we have in our data right here. Or another way of saying that is we're going to try to identify the frequency of each one of these numbers. So what's the frequency of the number 1 in our data set? 3. Right? We have 1, 2, 3 of them. So what we're going to do is we're going to say, hey, here's 1, 2, 3. We're going to go up to 3, and we're simply just going to make this little box-looking thing over the number 1 up to a height of 3. What's the frequency of the number 2 in this data set? 6. We have 1, 2, 3, 4, 5, 6. So 4, 5, 6. All the way up to here. I'm going to go up to 6. Everybody get the gist of what we're doing up here? All right, then how about you guys complete this frequency histogram for the rest of the data? Anybody need a little extra time? All right, let's finish this one off together. How many 3s do we have? 3 of them. How many 4s do we have? How many 5s do we have? And how many 6s do we have? So it looks something like this. Cool. Any questions about this frequency histogram? Everybody get the gist of what a frequency histogram is doing? It's just another visual representation of what your data looks like, right? If you never saw this data and you just saw this frequency histogram, you could easily say that the most frequent number that you have is the number 2. You don't have a whole lot of 5s in there, right? Is everybody good with this? So if this was, I don't know, if this represented the age of students in a class, right? What kind of school are you describing? Yeah, maybe like maybe even like a preschool or something like that. Maybe it's like a daycare center or something like that, right? Where like these kids are just kind of like hanging out or something like that. They're there to pick up their younger sibling. I don't know. Maybe you're gonna send like a 2-year-old home with a 6-year-old, but that doesn't sound safe, right? Like, yeah, hey, here you go, right? No, that wouldn't be good. Anyways, you guys get the gist of how this is a graphical representation of the data. So even if you had this huge, long list of data, having something like this is going to give you a picture of what your data looks like. Cool. All right. So let me pause here then, and then go back to the question that was raised earlier about comparing this to the data frequency table. The similarity between a frequency histogram and a data frequency table, the one that we described yesterday. Let me put that one back up here so everybody knows exactly what we're talking about. we made this thing yesterday, right? This table right here, and that is our data frequency table. In our data frequency table, what we did is we identified the possible values that we could have for x, and then we recorded how many times we saw each one of those possible x values. Right, everybody remember this? Does everybody see the similarity between the data frequency table and the frequency histogram, right? There's no coincidence there that both of them have the word frequency in it. Here we're looking at the frequency, and here we're also recording the frequency, right? Everybody good with that? Now, I think that these two, in my personal opinion, these two right here are much more closely related than the stem and leaf diagram. And then that's why whenever you said, hey, aren't these two things similar, the main difference that I see here is this. Whenever we're making the stem and leaf diagram, we're writing the numbers that we have in this category right here, right? Like we have the number 20, the number 20, and the number 28. What we're not ever really doing here in the stem and leaf diagram is being explicit about the fact that the frequency of the number 20 is 2, right? You can see that from up here, but we're not really making it necessarily explicit. So you're right that they're both data visualization techniques, and if you see the similarities between those two more than I do, that's completely fine. But you also see their differences. Everybody's good with their similarities and differences? Awesome. Any questions about the frequency histogram? All right, then the relative frequency histogram is by far the most commonly used visualization technique anytime that you use any kind of data, right? Or really anytime that you use any kind of statistics, especially out in the real world. Now, the good thing about the difference between the frequency histogram and the relative frequency histogram is that there's only a very, 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 very small difference, right? In order to help illustrate that difference, what I'm going to do is I'm going to write all these numbers up here that I probably should have written earlier on this y-axis that represented the frequency. And let me ask you guys this. Before we go and actually make this relative frequency histogram, what is the difference, and this is something that we talked about yesterday, what's the difference between frequency and relative frequency? What's the difference between frequency and relative frequency?
Isn't frequency the amount of times like a number occurs, while relative frequency is like the number of times it occurs divided by the total amount?
Exactly right, right? So the frequency is just how often something occurs, which is why here we're recording on this y-axis right here, we're recording how often something occurs, right? So we literally just go through and say 1, 2, 3, and that's how many times we count. For relative frequency, what we always did was we created some fraction, right? The fraction that we created, just like you said, was how many times that a number occurred divided by the total number of numbers that we had, right? Again, if I put this up here from what we did yesterday, whenever we created this data frequency table, we recorded the frequency of these things. Whenever I asked you guys to calculate out the relative frequency, say, of the number 5, then up here in the numerator, you had how many 5s that we had. We had 4 5s in this data set, divided by the total number of numbers that we had. Right? Does everybody remember how we calculated out the relative frequency? So then, if on here in this graph, if this is our frequency histogram, what would we have to do then to change it into a relative frequency histogram? Divided by the total numbers, right? So here we wouldn't say that there were 3 number 1s. The only thing that we would really say is that there are, well, how many numbers do we have here total? 17. You have 17? We would just say that 3 out of 17 would be the number of, or the proportion of 1s in this data set, right? So I'm just dividing it by the total number that we have. Here, it would be 6 out of 17. Here, it would be 5 out of 17, and so forth, right? Over here on the y-axis, we simply just have a proportion instead of the actual frequency of these individual values. All right, is everybody good with that? So now, if I said, hey, if you look at this graph now that I divided all these things by 17, which is the total number of numbers that we have right here, if I said, what's the relative frequency of the number 4, you could just say it's 2/17. Right, is everybody good with that? This relative frequency histogram is by far one of the most commonly used data visualization techniques in statistics or just in the real world in general, right? It's always going to report to you some kind of proportion. In fact, from here on out, especially after we get out of chapter 2, whenever we're going to try to represent our data, we're always going to use the relative frequency histogram. Later on in the semester, we're going to learn a really, really important distribution called the normal distribution. And the normal distribution is a relative frequency histogram. It's a little bit of a misnomer because it's not necessarily a histogram per se, but the y-axis is always reported as a proportion, not as a frequency. All right. Any questions about these data visualization techniques so far? All right. Then let's go on to the next page. Also, especially because the summer semester is such a short semester, so you know where to spend your time studying. I'm never going to ask you to make like a histogram or a relative frequency histogram or anything like that. You primarily just have to know how to read them, right? Like I said before, all the questions on your exam are always going to be multiple choice questions. So therefore, you might get some kind of data visualization, and you're going to have to say something about that data, and then just choose the appropriate answer choice for that. Right? So don't go home and try to make really neat boxes for histograms and stuff like that. You're just going to be wasting your time. Everybody good with that? Any questions about any of this stuff so far? How you guys doing with this stuff? Not bad? Cool. All right. One of the things that we're going to start to get into is we're going to start to get into a lot more formulas. And like I said, a lot of these formulas are included on the formula sheet that I gave to you previously. But as you start to look at some of these formulas, there might start being some symbols that are new to you, and you might not quite be sure how to read those symbols. So in order to make sure that everybody's on the same page, what I'm doing right here in this first portion up here on the next page is just to take a quick aside into math notation. We're going to practice how to read these symbols and exactly what these symbols mean to make sure that everybody's on the same page. If after we go over this, if these symbols still don't make sense, please let me know. It's important that you understand what these symbols mean before we move on, and I want to make sure that everybody's on the same page before we move on. Cool. All right. So first things first. Suppose that we have a data set, and here's just another way of representing a data set. The way that we've represented it so far, I just had a list of numbers. Now I'm just putting brackets around it. There's really no difference, right? It's just different ways to list data as well. Suppose that we had the data set, and the data set consisted just of the numbers 1, 2, and 3. Then for number 1 right here, we see a symbol, and it says this symbol X is equal to something, and it wants us to find out what that is equal to. Who knows what this symbol is right here? Anybody know what it is? It's sigma, right? It's an uppercase sigma. Does anybody know what that represents in math? The sum, right? It means the sum. So it's the uppercase sigma, and whenever you see the uppercase sigma letter in mathematics, it simply just means the sum, right? So this right here is known as the summation symbol. And what the summation symbol says is this. Summation symbol says everything after this, add them all up together, right? So whatever we have after this, after the summation symbol, it wants us to add them up. So here it's saying add up the values of X. So now your next question probably is, okay, well, what are our values of x? Whenever you have a data set, you can imagine these numbers in here to be your x values. So for any data set, we're always going to imagine that inside our data set we have x values. This x value is simply just the number 1. This x value is the number 2. This x value is the number 3, and so on and so forth. So they're just different realizations of the x, the symbol x, right? So what it's telling us then here is if we want to sum up all of our x's, what are we going to do? Just add them up. So basically what it's telling us to do here is to take 1 plus 2 plus 3. And I think everybody will agree that 1 plus 2 plus 3 is equal to 6. And that's the sum of x. Everybody good with the sum of x so far? All right. Now, remember that this summation symbol is just the same thing as addition. So that the usual order of operation in mathematics still holds, where stuff that comes before addition, you still have to do that stuff before addition, right? It's always multiplication and division first, and then you do addition and subtraction. You always do what's in parentheses first before you do stuff that's outside. You guys remember like the orders of operations and stuff, right? So whenever we see this summation symbol, just remember that it's nothing more than addition, but you still have to follow the orders of operations, the rules of orders of operations. Right? Is everybody good with that? So then if we go down to number 2, it says the sum of x squared. So what are we going to have to do first? We're going to have to square the numbers, and then we're going to add them together, right? So what we're going to have then is we're going to have the number 1 squared. We're going to take the number 2, and we're going to square it. And we're going to take the number 3 and square it. And after we square those numbers, we're going to add them together, so we're going to get this right here. Everybody good with this? So then here we're going to have 1 plus 4 plus 9, which is equal to 14. Any questions about number 2? All right, then in number 3, what's going to be our order of operation? Good. So we're going to do the parentheses first. So we're going to take our x values and we're going to subtract 1 from each of them. And then you said the exponent, and then whatever's inside there, we're going to square. And then what's last? And then you add them all up because it's summation symbol. Awesome. So what we're going to have then is we're going to have 1 minus 1 squared plus 2 minus 1 squared, right? Our first x value minus 1 and then squared, and then our second x value minus 1 and squared, and then our third x value minus 1 and squared, and then we're going to add all these things together. Is this making sense to everybody? All right, and if we do this, it's going to become 0 squared plus 1 squared plus 2 squared, which I think everybody will agree is the number 5. How do you guys feel about the summation symbol? Any questions whatsoever about how to read the summation symbol, especially if it's in some kind of formula? Any questions whatsoever? Everybody's good? All right. Then from here on out, I'm going to assume that you guys understand how to read the summation symbol whenever we're looking at different formulas. All right. So our first formula that we're going to look at is the definition of a sample mean. This right here is our formula for the sample mean. And really, 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 really importantly, x bar is the symbol for the sample mean. So here's our formula for the sample mean, but importantly, x bar in particular is the symbol for the sample mean. This is something that's going to be really important for you guys to remember. That the symbol for the sample mean is equal to x bar. Right? The symbol for the sample mean is x bar. That's definitely something that you're going to have to remember. So much so that on the first exam, and probably also on the homework, you're going to see questions that say, calculate x bar. That's it. That's all it's going to tell you. And if you don't know what x bar stands for, then you're not going to be able to answer the question. Right? On the test and the homework, I'm never going to throw curveballs at you, right? I'm not one of those teachers that says, I'm going to teach you 95% of the stuff, and that extra little 5% of the stuff I want to see if you can figure out for yourself on the test. That doesn't make any sense to me. What I'm going to do is I'm going to tell you the guys the stuff that you need to know, and then I'm going to ask you a question to see if you know it. That's basically all that I do, right? So I'm telling you, you need to know that X bar is the symbol for the sample mean. And let me be really explicit about it. The way that you pronounce this symbol right here is X bar, right? It's like an X with a little line over it, and that's called X bar. Yeah?
Not that that's like hard to memorize. Do we get this on the exam?
You get that formula sheet on the exam. I will always provide you with that formula sheet because what has happened in the past is people have made little notes on those formula sheets, and then obviously that's an unfair advantage. So staple to the front or to the back of the exam, you'll have that formula sheet. Exactly. Great question. Everybody good with the symbol for the sample mean is X bar? And here's the formula for it. All right. And then obviously the mean here, if you look at this stuff right here, we're going to sum up all of our x's just like we did in example number 1 up here. And now we're dividing it by this little n. So let's talk about little n because little n is really, really important too. Little n is the size of your sample. So let's say here, for instance, and this is something that we kind of talked about last class, right? Where we had a population and we had a bunch of things in this population. I kept referring to like the average height of students at UNC Charlotte and so on. And then I said from this population, we would take a sample. And then a sample was some subset or some sub-collection of our population. How many things are in our sample? That is what little n represents. So if our student population at UNCC is 30,000 people, and we decided to measure the height of 1,000 of them, then 1,000 people are going to go into our sample. Then little n is equal to 1,000. Right, is everybody good with that? If all of the classes that here in Fretwell that are having a class that starts at 9:45 a.m., of all those students, I don't know how many that there are, but let's say there's like 300 of you, right? And if we took this class as being a sample, then our sample size would be, well, today it's 14. Then little n is going to be the number 14. Everybody good with what little n represents? Really, really, really important for you guys to also remember that little n is the size of your sample. Right? So little n is the size of the sample, or how many things are in your sample. Everybody go with this first formula so far for the sample mean? All right, then our next formula is that for the population mean. The population mean looks really, really similar, especially if you just look at that formula. The sum of x over capital N. The only real difference here is this capital N. So if little n represented the size of the sample, what do you think capital N represents? Size of the population, right? So capital N is the size of the population. Which if you think about these two formulas, if you just look at the formulas, it should make intuitive sense to you, right? Let's stop here and think about this. If I asked you to calculate out the average height of everybody in this classroom, what would you do?
Measure each person and then divide by the number of people.
That's right. Measure the height of each person, add up everybody's heights, right, and then divide by how many that you have. That's exactly what we're doing right here. We're measuring each person, we're adding them all up, and then we're dividing by how many that we have. If it's a sample, and here we're just using different symbols if it's a population, right? The whole gist behind these formulas is exactly what you understand the mean to be, and I'm sure that a lot of you are now recognizing that the mean is nothing different than the average. The average. Oh gosh. I think I'm missing an A. But I have such atrocious handwriting that you probably didn't realize that I was missing an A. Right? Oh, and you can't see it. All right, great. Had I not said anything, I could have gotten away with one. Better luck next time. Everybody good with calculating out the average for a sample and for a population? All right. Then, another thing that I want to mention here is that it's also really important for you guys to remember that this right here is the symbol for the population mean. Does anybody know what this symbol right here is called? Mu? Good. So it's pronounced here mu. I've seen some people write like M-O-O for like, it's mu, it's not really mu. But maybe it is. Maybe I've gotten it wrong. But I pronounce it mu. All right. So here it's important for you to remember that this symbol is the symbol for the population mean. If you forget that it's mu, it's no big deal. We're going to use it about 50,000 times in the next 5 weeks, so you'll remember that this thing is called mu. But then let's also try to remember some of the vocabulary that we learned in Chapter 1. Here we have a symbol representing the sample mean, and this symbol is not a Greek symbol. But here we have a symbol that represents the population mean, and this is a Greek symbol. So if you remember last class we learned 2 vocabulary words. Which vocabulary word would apply to this one up here? X bar is an example of what? It comes from a sample, but it's a statistic. Good. X bar is an example of a statistic. It's a number that you're calculating out from a sample. And any number that you calculate out from a sample, or some measure that summarizes a characteristic of a sample, that is a statistic. And this thing right here is a number that we're calculating out from a population. So therefore, this is an example of what? Mu is an example of a parameter. Awesome. So here, I'm going to write this is a statistic, and this is a parameter. All right, everybody good with these formulas? All right. So let's go then to the definition of a sample median. The symbol for the sample median is this symbol right here. It looks like an X with like a swoosh over it. And the way that does anybody know how you pronounce the symbol? It's X tilde. X tilde. It's a symbol for the sample median. Later on in the semester, we're going to come across another topic that uses X tilde. Other than that, we pretty much don't use X tilde at all after we get done with Chapter 2. But later on in the semester, I'm going to ask you guys, because it's going to come up once again, I'm going to say, hey, what's the name of the symbol? And every single semester, it's always like one of the most commonly forgotten names for symbols. Except for one time I had a class, this was about 2 years ago, and I said it was called X tilde. And there was a girl that sat in the first row, and she goes, that's my middle name. Tilde was her middle name, right? So anytime that I asked it, she would always be like, oh, it's tilde, X tilde. So she always nailed it. But other than that, usually whenever we get to this topic later on in the semester, it's one of the most commonly forgotten names for symbols. So obviously, it's not super duper important to remember that it's called X tilde, but it is important that you guys understand what the sample median is. So let's talk a little bit about the sample median. The sample median X tilde of a set of sample data for which there are an odd number of measurements is the middle measurement after the data are arranged in numerical order. So I'm going to stop right here, right? That's like the first part of the definition. The sample median X tilde of a set of sample data, whenever there are an odd number of measurements, it's going to be the middle value whenever you arrange the numbers in numerical order, right? So then the definition continues, and it says that the sample median x tilde for a set of sample data whenever there are an even number of measurements is the mean of the two middle measurements after the data is arranged in numerical order. So we really have two definitions included in one definition here. One is whenever we have an odd number of measurements, and one is whenever we have an even number of measurements. Whenever we have an odd number of measurements, we can just use the middle value as the sample median. But whenever we have an even number of measurements, we have to take the average of the two middle numbers. If this definition isn't making a whole lot of sense to you yet, don't worry about it. We're going to do some examples about this here in a minute, and I'll make sure that I highlight this so everybody's on the same page with this. Just keep in mind, until we get there, that whenever we're trying to find the sample median, we have to do something different if we have an odd number of measurements versus whenever we have to have an even number of measurements. All right. Then another one of our important descriptive statistics is the sample mode. The sample mode is simply, in a set of sample data, the most frequently occurring value. And here I want to highlight that it's the most frequently occurring value. It has to occur more frequently than something else, and not just more frequently than something else, but it has to occur most frequently, right? So there's like two steps there, right? It's not just that it has to occur as frequently as something else, but it has to be most frequently. All right, so let's go on and do some examples of these descriptive statistics. If those definitions aren't making a whole lot of sense yet, don't worry about it. After we get done with these examples, I'm sure it's going to be a lot more clear. All right, so use the following sample data to calculate out the sample mean, median, and mode. So let's start off with the sample mean. What's the symbol for the sample mean? X bar. And then our formula for the sample mean is the sum of x divided by little n. If we wanted to do this formula, how could we write, like, if you want to show your work, how could we be explicit about this formula? What would you write down in order to show your work? Going to add them all up. So we have 4 plus 3 plus 7 plus 5 plus 1 plus 2, and then all the way to the end. And then what would be our next step? Divided by how many that we have, and how many do we have? How many? 11. I'll save you guys the arithmetic on this. This is going to come out to 77 divided by 11, which is just equal to 7. Everybody good with this? Cool. So there we have now our sample mean. Next thing it's asking us to do is to find the sample median. What's our symbol for the sample median? X tilde. All right, and remember this is the part, the descriptive statistic that we have to do one or the other thing depending on what. What are we looking for whenever we're trying to calculate out even or odd numbers, right? So do we have an even or odd number of things up here? Odd, right? We already said that we had 11 of them. So if we have an odd number of values, what are we looking for? The number in the middle, but after what? After it's in numerical order. So therefore, our first step is to do what? Put them in numerical order. Cool. So if we put them in numerical order, then here we're going to have the number 1. Then we're going to have the number 2, the number 3, the number 4. We have 2 number 5s. Then we have the number 6, the number 7, the number 9, the number 15, and the number 20. Everybody good with this? All right, so now we need to identify the middle number. What number's in the middle? 5. And to be really explicit about it, it's this 5 right here that's in the middle, right? So we have 5 numbers on one side, we have 5 numbers on the other side, so therefore it's this 5 right here that is in the middle. And it's really important to identify this 5 right here as the median. Everybody good with that so far?
So if there's an even amount of numbers,
Great question.
the average of the middle two.
Then we would have the average of the two middle two. And I believe that that's our next example. Cool. All right, everybody good with the sample median? Get an odd number. Whenever we have an odd number, after we arrange it in numerical order, we select the middle. All right, the mode. Sample mode. What's the symbol for the sample mode? Not X bar. It's not on there, right? It doesn't happen. It's not just that I left it off the notes. Whenever mathematics was being established, like for some reason, it just didn't get a symbol. Or at least none that I'm aware of, right? So this does not have a symbol. But whenever we're looking for the sample mode, what are we looking for? The most frequently occurring value. So in this data set right here, what is the most frequently occurring value? 5. Right? All other values only occur once, and therefore, except for 5, 5 occurs twice, so therefore the sample mode is equal to the number 5. Everybody good with this so far? All right, so let me ask you guys this. How many modes could you have? What's the most number of modes that you could have? If you could think of any data set that you wanted.
Wouldn't it be infinite?
Wouldn't it be infinite? All right, so let's think about that, right? Let me flip this over. Here, we just had an example where we had one mode, right? Similarly, let's say that we have a data set that has the number, let's say that we have the data set that has the number 1, 2, and 3. If we have a data set that has the numbers 1, 2, and 3, it just replied it to me. I hope it's not going to have a lag now. Anyways, if we have the data set that just has the numbers 1, 2, and 3 in it, which value occurs most frequently? None of them occur most frequently. So therefore, do we have a mode? No. So here, in this case right here, we have no mode. Right? Is everybody good with that? But let's say that we change this right here to the numbers 1, 1, 2, 3. Now which value occurs most frequently? 1. So therefore, we have one mode, and that one mode is the number 1. Right, is everybody good with that? If we have a data set that's 1, 1, 2, 2, 3, how many modes do we have? 2 modes. And what are the modes? 1 and 2. Now, let's say that we change this to 1, 1, 2, 2, 3, 3. How many modes do we have? Which one occurs most frequently? None of them occur most frequently. So again, we're right back to no mode. You guys get the gist? We could go on and we could change this to 1, 1, 2, 2, 3, 3, and 4. Now how many modes do we have? You guys get the gist, and so on and so forth. Then if I added another 4 right here, we're right back to no modes. So you're right. If I said, hey, we could make any data set that we wanted to, we could just keep going, right? We could add 2 5s, 2 6, 2 7s, 2 8s, 2 9s, and so on and so forth. As long as at the very, very end, we just added in a single number. Or similarly, we could also just have a 0 right here, or put like a -1 right here, or something like that, right? So you can go positive and negative. We can come up with a data set that just keeps going on forever and ever and ever. So technically speaking, we could always have an infinite number of modes. So it's possible to have no modes, possible to have 1, 2, 3, or however many modes we want. Always has to be a whole number, right? Because we're counting things. But we could go all the way up into infinity as well. Everybody go with most frequently? That's why whenever we went over that definition, I tried to highlight the fact that it's most frequently. All right, let's go on to this next example. We want to calculate out the sample mean. Take a minute for yourself and see if you can calculate out the sample mean for the second example, and try to write it exactly as I wrote it up here. Try to get in the habit of writing the symbols and the formulas for these things as well. Yeah, actually, while you guys are at it, also do the sample median for this problem and the sample mode. All right, does anybody need a little extra time? How you guys doing with this? Good so far? All right, so let's do it. So the sample mean then has a symbol of x bar, and x bar has the formula of the sum of x over little n, which means that we want to add up all of these values in the numerator and divide by how many that we have in the denominator. So here we're going to add up all the ones in the numerator. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. And if you do this arithmetic, you should again end up with 77 in the numerator, now divided by 10 in the denominator. So for a sample mean of 7.7. Everybody good with a sample mean of 7.7? The sample median then is the next thing that we need to do. And whenever we want to figure out what the sample median is, what's an important first step that we have to do? Put them in numerical order. So if we put them in numerical order, we're going to have 1, 2, 3, 5, 7, 8, 9, 10, 14, 14 and 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. And now that we know that we put them in numerical order, and we also recognize that we have what up here? An even number of values, right? So here this is different than the example that we did before. Here we have an even number of values. Whenever we have an even number of values, how do we identify the median? Awesome. We take the average of the two numbers in the middle. So here we have the two numbers in the middle. So therefore the median is going to be the average of these two numbers, or 7 plus 8 divided by 2, or 15 divided by 2, which is 7.5. That's going to be our median. What's the symbol that we're going to use for the median? X tilde. So here then X tilde is equal to 7.5. Everybody good that the median is equal to 7.5? Then for a sample mode, what are we looking for the sample mode? The most frequently occurring value. Which value is the most frequently occurring value? We don't have one, right? They're all only occur once. So therefore here we have no mode. Everybody good with having no mode? All right. So that's the second example. One of the things that I want to do here is I want to go back over how to calculate out the sample median. Because what I've noticed in the past is the way that people do this, whenever they get it wrong, they always do the same thing. Like the vast majority of people always do the same thing wrong, right? So I want to show you what people do whenever they get this wrong. Most of the time what they do whenever they get this wrong, so that you don't do that mistake, right? So what I'm about to show you is completely wrong, so you know that it's wrong and that you don't do it yourself. So this is what people do. Usually what happens is this. On a test, right, if you just had a set of numbers like this, it would be easy for you to see that there are 10 values here, and then it would be easy for you to identify what the two middle values are, and then to take the average of those two. But on a test, it's usually different. They don't just give you 10 values. On a test, sometimes you're given like 90 values or something like that, right? So it's like this huge, long list of numbers, right? And they're usually in order. They usually do that for you. But then they say, hey, find the middle two numbers. And if you just had this huge, long list of numbers, what people frequently do is they do this. And now this is wrong, and this is why I'm telling you to do this. They see all those values, and usually like a little bit of panic probably sets in, right? And they're just like, oh crap, how am I supposed to find the middle value? And then this is what they do. They go, well, I need to find the middle value, so I'm just going to cross off one on one side, one on the other. I'm going to cross off, and I'm just going to keep crossing off on both sides until I just end up with one value, and that's going to become my median, right? So then they identify here that this was their median because they said, well, I just kept crossing off one from each side, so the number that I'm ending with has to be the median. Now, why is that wrong? Because they don't realize that they should have had an even number of values, and with an even number of values, you should end up with two values. And as you can recognize here, 5 numbers were crossed off on this side, but only 4 numbers are crossed off on this side. So it tells you that this number 8 shouldn't be the middle value, right? So that's something that I see very, very, very frequently whenever people get these things wrong. This is a completely wrong way to do it, and does everybody recognize why this is wrong? Cool. So definitely don't do this. All right. Other than that, is everybody good with the second example? How do you guys feel about these types of problems? Anybody want to do this last example down here? Are you guys good to go with finding the sample mean, median, and mode? Anybody want to do it? Going once, going twice? Everybody's good? All right, then we'll skip this one. All right. Next thing that we're going to look at is we're going to look at the definition of symmetric, skewed left, and skewed right distributions. So, first off is this. This distribution thing, you can think of this as any kind of histogram or relative frequency histogram. So either a frequency histogram or a relative frequency histogram. That's really what a distribution is. Now, most commonly, whenever you hear the word distribution, since the relative frequency histogram is by far one of the most commonly used data visualization techniques in statistics, especially in the real world, when any kind of sophisticated statistical analysis is done of any kind of data. Relative frequency histogram is the most commonly used one. So therefore, as we're describing distributions, we're always just going to start making use of the relative frequency histogram. That's particularly in this case because, like I said earlier, after we get out of Chapter 2, the only data visualization technique that we're ever really going to use is going to become the relative frequency histogram. So we're just going to start using that one exclusively as well. All right. So let's take a look at the three different kinds of distributions that we can have. We can have a symmetric distribution, or we can have a skewed left distribution, or we can have a skewed right distribution. So before we look at the comparisons between the mean and the median over here on the right of these definitions, let's first talk about what I'm sure you already understand is, what is something that's symmetric? If you had to describe what it means for something to be symmetric, how would you describe it? It's a mirror image, right? Like the left-hand side is the same as the right-hand side, and so on and so forth. So therefore, an example of a symmetric distribution could be a distribution that looks like this. That is a Picasso-esque description of what a symmetric distribution can look like, right? Perfectly drawn, perfectly symmetric, right? No, I get one person smiling, the others are just kind of like, all right, dude. Another example of a symmetric distribution could be something that looks like this, right, where there's just one peak in the middle. It could be an example that looks like this. Right, is everybody good with what a symmetric distribution looks like? Left-hand side is the same thing as the right-hand side. All right, so then let's take a look at a skewed left distribution. A skewed left distribution is one that looks like this. This is the textbook example of a skewed left distribution. And then the textbook example of a skewed right distribution would be the one that looks like this. So this one up here is skewed left. The one at the bottom is skewed right. So let's take a look at these because there's a couple of definitions that go along with this that aren't necessarily mentioned in the textbook that accompanies this course. And that's this. Here, if we look at any distribution, the distribution is going to have a left-hand side to it over here and a right-hand side to it over here. Same thing if it's symmetric or if it's skewed right. Whenever we have this side of a distribution, this is known as the tail of the distribution. And same thing over here. This right-hand side is also known as the tail of the distribution. The ends of the distribution are simply just known as the tails of the distribution. Right, is everybody good with that? So same thing over here. We have this tail of the distribution here, and also this. This is also the tail of the distribution. A distribution is skewed left whenever this bigger side over here is on the left-hand side of the distribution. Right? This is known in statistics, and this is the technical term for it. This is the fat tail of the distribution. Right? The fat tail of the distribution here is on the left-hand side of the distribution, so that's why it's skewed left. And then on the bottom, the fat tail of the distribution is on the right-hand side of the distribution, and that's why this distribution is skewed to the right. If the distribution has neither a fat tail on the right or on the left, or if both sides have one on the left and the right, particularly if it's symmetric everywhere else, then it just would be a symmetric distribution. Right? Is everybody good with the fact that these things right here are the tails of the distribution, and wherever the fat tail of the distribution is, particularly in these two examples, that's going to be the direction of your skewness. All right. Everybody good with symmetric versus skewed left versus skewed right? All right. Now let's try to take a look at the ends of this of these definitions, rather, and see exactly what these things mean. Let's first look at these numbers right here. Right. So let's have the numbers. -3, -2, -1, 0, 1, 2, and 3. If we had a distribution that, if we make this into a frequency histogram, if we had a distribution that maybe looks something like this, where it's symmetric. Right, so that's my best shot that I could do at being symmetric. Right? If you wanted to make this as a line, it would look something like this. But it's basically supposed to be symmetric on both sides. If it's symmetric on both sides, right, and it's centered right here on the number 0, what is going to be the average of all of these numbers in here? What do you guys think? If it's a symmetric distribution, the average is going to be 0, right? So let's think about this here. Let me flip it over. Let me make it a little bit different. Let me take a step back and let me talk about exactly what a distribution is. Suppose that I handed out pieces of papers to all of you, and on these pieces of paper, I asked you to record how many times on average in a month you call your mother, right? And so then you wrote down a number on this piece of paper, and then after you wrote down the number on this piece of paper, I collected all these pieces of papers again. And then I said, okay, let me try to plot these numbers. So let's say that the least amount of times that you could call your mother on average in a month is 0. And if you wrote 0 on this piece of paper, right, shame on you, right, call your mother. But let's say that the most number of times in a month that you could call your mother, let's just say it's 30. Let's say you can't really call your mother more than once in a day, but if you do, good for you. So then I take these pieces of paper, and I just go through them one by one. Maybe the first person I come across, maybe they called their mother 15 times in a month. So then I'll make a dot above the number 15. And then I go on to the next piece of paper, and the next person said that they call their mother 25 times in a month, so I'll make a dot above 15. The next person maybe just called their mother 5 times in a month, I make a dot above the number 5, and so on and so forth. You guys get the gist of this? Now, let's say I come across another person that also says they call their mother 15 times in a month. What I'm simply going to do is I'm simply just going to make another dot above the number 15. So it almost becomes like Connect 4, right? Like you're dropping like these little chips down like these little shoots, right? Or if you're my nephew is 3 years old. He doesn't quite understand the idea of dropping them down into things. He's more of like he wants to shove them down in there, right? And he doesn't quite understand yet the concept of turns yet either, but that's a completely different story. Everybody's good with what I'm trying to do up here with plotting these numbers, right? So I'm going to go through, and there's 15 of you. I have no idea how this is going to end up, but let's just say that it ends up with something that looks like this, right? This right here is a perfectly fine representation of what a distribution looks like, right? Because what we could do is we could turn this into a histogram, depending on if we had the numbers 1 and 2 up here, or we could turn it into a relative frequency histogram if we said that this was out of 15, since there are 15 of you in this class, and so on and so forth, right? So whenever you hear the word distribution, try to remember back to this idea of like you're dropping like these little Connect 4 chips into like these little shoots. That's basically what a distribution is, right? So now then, if we go back to what I was saying up here before, the question I was trying to ask is if we have a distribution and it's a symmetric distribution, so that here maybe we have one dot right here and one dot right here like we did in the previous page. Here maybe we have 2 dots. Here maybe we have 4 dots. And here maybe we have 6 dots, right? My question is what is the average of this distribution? Well, now one of the things that you could do is you could say, well, I could say that this is a -3 and this is a -3, so the average of that should be 0. This is a -2 and these are -2, so the average of these two things right here should be 0. And so on and so forth. So if you added up all of these numbers and you divided by how many that there were, you would end up with the average being equal to 0. Right? Is everybody good with that? So therefore, if you have a symmetric distribution, the average of that distribution is just right in the middle. Does that make sense? So here in this example, the average of the distribution would simply just be the number 0. So we know that the average, if we have a symmetric distribution, the average of that distribution should be right in the middle. Right? Is everybody good with that? But now let's think about that phrase. The average of the distribution should be the number that's right in the middle. Well, we know a different vocabulary word for the number that's right in the middle. What's the number called that's right in the middle? The median, right? So therefore, if the average of the distribution is the number that's right in the middle, then the average of the distribution is the median, right? So therefore, whenever we have a symmetric distribution, the average is equal to the median. Everybody good with that? And that's what this definition right up here says, that a symmetric distribution, the mean is equal to the median. Does that make intuitive sense now? All right. Then let's look at a skewed left distribution. So if we have a skewed left distribution, we have a distribution that looks something like this. So we have a distribution that looks something like this. Again, what I'm going to do is I'm going to color in these dots. And again, these dots you can kind of imagine, like we just talked about. This is like that example where, on average, how many times in a month you call your mother or whatever. There's a lot of dots right here in the middle where it's high, but then where it's low, there's only like a few dots. And let's say that we have one dot that's like way, way, way out here. Everybody good with this? All right. Let's look at the median first this time, right? We'll get to the average here in a second. Let's look at the median first. The median is simply just the middle number, right? Especially if we have an odd number of values, it's the middle number. Even if we had an even number of values, it's just the average of the two middle numbers. So instead of saying like this is the median, If it's odd number of values, it might be like the average of these two numbers. But regardless, you guys get the gist that it's still going to be like right here, right? So then, if I try to identify the middle value of all these dots, I'm just going to eyeball it here, right? I'm going to say this one right here looks like it's the middle dot, right? You might think it's a little bit more to the left or to the right, but we're just, it's just a general picture right here, right? So we're going to say that the median is going to be whatever value that is right there. Everybody good with this so far? Where would the average be? Do you think the average would be below this or to the right of this? Below it. So let's think about this here, right? Let's put some numbers to it so it makes it a little bit more explicit. Let's say that I had a data set, and my data set for all this right here, let's just say that this goes to, let's stick with how many times in a month. Well, let's not stick with how many times in a month you call your mother. Let's make it a little bit different. Let's say that this is, let's make it fun. How much money you have in your bank account, right? That's a good one. And the best part, the way that we're going to make this fun, is we're going to say that this upper end right here, this is like $5 million, right? $5 million in my bank account. What would you guys do if $5 million was in your bank account? Not be right here, right? No, heck no, right? Somewhere really nice. All right, anyways, we're getting off topic again. But here what we can see then is, and then over here we have something that's really, really low. And, I don't want to single out any of you guys, so I'll make myself the brunt of the joke, and we'll say that this right here is my bank account, and we'll say that in my bank account I have negative $1 trillion. I don't know who is better off, you having $5 million in your bank account or me having negative $1 trillion. Probably just means that I had a really good life so far, right? Like if I could have spent $1 trillion, right? Man, at least I'm teaching stats and not a finance course, right? Like I shouldn't be a finance professor then yeah. Anyways, getting off topic, right? Everybody gets a gist. If we wanted to list out the numbers in this data set, then, some of you are just down here, so some of you might only have like $1 million in your bank account. That's too many zeros. Right, we might have like $1 million, then the next person might also have $1 million. You guys get the gist? Then the next person might have $2 million. And then we're going to have a whole bunch of people in here. So let me just write this in terms of millions, right? Might say that one person has 1 million, one person has 1 million, then a couple people have 2 millions, then a whole bunch of people might have $3 million, so I'll make 3, 3, 3, 3. Next people have $4 million, a whole bunch of 4s, and then a couple people have $5 million again, right? But now the problem is that I don't have negative 1, I have something that's like negative 1,000. Or I guess if it's $1 trillion, it would be like a negative 1 million. So this number right here, this last number, that's me. This negative 1 million, right? What am I doing to the average? I'm like bringing the average way, way, way down, right? So I just have one number that's all the way here, all the way to the left. But that number is huge. So what I'm doing to the average is I'm bringing the average way, 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 way down. Right? Is everybody good that I'm bringing the average way down? So therefore, the average is going to definitely be less than the median. Like the average might be like somewhere like way over here, right? So this might be the average. Is everybody good then that on a left skewed distribution, the average is going to be less than the median? Does that make sense? So that's why we have here a skewed left, that the average or the mean is less than the median. You could do this exact same thing, just going the opposite way around. Let's make the numbers a little bit easier to look at this time. Let's say that we had over here, we had a whole bunch of values that were between 0. So here might be like the value 1, here's 2, here's 3, and here's 4, and then so on and so forth. So here, we're then going to have a whole bunch of 1s. We're going to have more 2s than we have 1s. We're going to have a decent amount of 3s, a few 4s. But then again, we're going to have some value that's way, 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 way over here that might be like 1 billion. Is everybody good with the fact that, first of all, this right here is a right-skewed distribution? Does everybody then agree then that this one number all the way out here, that's going to explode your average? So therefore, you might identify this one right here as being the median value, but because you have this one number over here, the average is going to be significantly higher. Right, is everybody good with that? So therefore, the average is greater than the median. Does that make intuitive sense? So then if you go back to these definitions right here for symmetric skewed left and skewed right distributions, everybody good that why this is the mean is equal to the median is less than the median, and the mean is greater than the median? Everybody good with this? All right. Then the next things that we're going to get into is we're going to get into measures of variability. But measures of variability is a whole new section. What we just got done doing is talking about measures of center and location. These ones right here are completely different, so we'll just pick up there on tomorrow. We have class tomorrow. Cool. All right, I will see you guys tomorrow then. Have a good one.